Welcome back. All right, this is part two of section three. So in the first part, we talked about magnetic field, magnetism. Now we're going to kind of shift gears a little bit and talk about mapping the ocean basin, mapping the bottom of the ocean. And then we're going to put both of those ideas together and figure out what they tell us. So, excuse me. Once we had the technology to begin to map the bottom of the ocean, which started around the 1950s or so, 60s, it's coming out of World War II. Submarines are kind of starting to become more of a thing. We're in the Cold War, so we start, mapping the bottom of the ocean to know what it looks like, so to make sure submarines don't run into anything. So what started to be revealed as we were mapping the ocean is that there's this massive system of mid-oceanic ridges that runs in a continuous range underwater, these large ranges of underwater mountains that wrap around the globe, kind of like the seams on a baseball, which are continuous. And it stretches for nearly 65,000 kilometers. It's the most extensive mountain range in the world, and it's all underwater. I'll show you a picture here in a moment. One of the most famous sections of that mid-oceanic ridge system is known as the Mid-Atlantic Ridge. Again, it's the best known part of the system, and it divides the Atlantic Ocean basin nearly in two. It kind of runs right down the center of the Atlantic Ocean on the seafloor. Looks a little something like this. It starts way north of Iceland, kind of up near the North Arctic, and it kind of runs down through the middle of the Atlantic. This is the Mid-Atlantic Ridge. All right. And so this is connected to a broader ridge system, but this is kind of the most famous section of that ridge system. And what we find happening at these ridge systems is that the seafloor is spreading apart along these kind of mid-oceanic ridges. The person that kind of stumbled on this, and then how it eventually relates to geology, is Harry Hess. He was a geologist and a Navy officer, and he was in charge of mapping the seafloor. Go figure. So in 1962, he kind of proposed the notion of seafloor spreading based on the maps that he was creating of the seafloor. So what he was saying is that, well, the seafloor spreads, and when it does, the oceanic crust, which is the crust usually under the ocean, which is connected to the continents, kind of move together. So if I'm spreading the seafloor, I'm going to spread the continents out that it comes in contact with as well. At these oceanic ridge systems, the seafloor separates at that point, moving away from each other. And that's also where new crust is going to form, because as the seafloor splits at this ridge center, once you open up that gap, hot magma and mantle material is going to ooze up into that crack, cool, to create brand new rock. So that's where new oceanic crust will be forming from this upwelling and cooling of magma. So once you spread these plates apart, something's got to fill in that gap. This magma kind of fills in the gap, cools, becomes brand new rock, brand new crust. And this crust then begins to move laterally away from the ridge. So you get this magma material filling in the gap, cools, becomes new rocks, and then kind of gets separated. So you have this new crust kind of getting separated, and the same stuff is kind of moving on either side away from the ridge. And then, we needed that mechanism of continental drift. This is where the idea that at these spreading centers, something below must be driving that, and that's where the idea of thermal convection cells, mantle convection, came into play. That's what must be kind of pulling these oceanic plates apart. So now we have a mechanism. We had some better evidence of movement, where it's happening, and why it's occurring. So again, that hot magma rises, forms new crust at these seafloor spreading sites, and then on the edges of the oceanic basins, then that older cold oceanic crust must subduct back down into the mantle. The reason being, we can't just create new Earth. We can't just create a new area and continue to do that over time. The Earth is only so big, can't get any bigger. So if I'm creating new crust in one area, old crust has to be kind of done away with. So where these plates are spreading apart, we're getting new crust, but where we get subduction of plates, and more on that in a little bit later section, then that plate, as it subducts, goes back down into the mantle, it heats up, and is recycled. So confirmation of Hess's, of Hess's hypotheses came in the form of, let's go back to the magnetic field stuff. So in addition to mapping mid-oceanic ridges, ocean research also revealed magnetic anomalies on the seafloor. So we kind of see similarities on either sides of these mid-oceanic ridges. But now, using something called a magnetometer, we can detect magnetic fields, very, very subtle magnetic fields, excuse me, in these seafloor rocks. So a magnetic anomaly is a deviation from the average strength or direction of the Earth's magnetic field, because remember, the magnetic field changes. The magnetic anomalies were discovered to be almost like visually, these stripes of parallel rocks, symmetric to the mid-oceanic ridges. So when we run a magnetometer, if this is the spreading center of the mid-oceanic ridge, on either side we see the same magnetic signatures in the rocks as we go further and further away. So therefore there must be the same rocks created at the same time at these oceanic ridges, and they just kind of spread apart. What that kind of looks like, if we can imagine it visually, the colors are just there to show you either normal magnetic polarity, where north is pointing one way, or reverse magnetic polarity where north is pointing the opposite way. So imagine, say, 15 million years ago, all right, we have the some mid-oceanic ridge, new magma's kind of coming up, cooling, creating brand new rock, brand new crust, and this light tan. So at that point we had a magnetic reversal. And then as land continued to spread away, you can see the magnetic field flip back to normal, and then at 9 million years, it must have flipped back, reverse, magnetic reversal, because now we get this new material coming in. And then between 9 and 3 million years ago, it flipped normal. Then 3 million years ago, it flipped back to reverse. It's not that the seafloor has different colors. Again, it's just to illustrate the different rocks when the magnetic field's in different locations. So essentially, like if you're kind of visualizing this, it's almost like the rocks were striped in that we can see the magnetic fields kind of flipping back and forth on either side and symmetrically. So movement occurs at these mid-oceanic ridges as driven by mantle convection. So there we go. All right. Now we've got a mechanism and a reality to some of these ideas of the continental drift folks, including Alfred Wegener. So what we can find once we started sampling oceanic crust, again, it's very young. So the seafloor spreading indicates that oceanic crust, again, is very geologically young, because if you have molten rock, it's not rock yet, it's hot liquid. Once it cools, it's brand new rock, 0 million years old. The material that makes up that rock is old, but the rock itself is a brand new rock. So oceanic crust is geologically very young, and it forms during spreading, as that happens continuously. Oceanic crust, seafloor crust, is destroyed during subduction. We can radiometric date rocks. That's using some fancy science equipment and radioactive material in the rocks to put a date to it. It's very reliable. So radiometric dating is a scientific process using fancy equipment, and it confirms that the oldest oceanic crust is less than 180 million years old. Think back to Lab 1 on geologic time. That's not much time at all, right? The Earth is over 4.5 billion years old. 180 million years isn't really all that old. So the newest oceanic crust is 0 years old. It's brand new. The oldest we can find on Earth is around 180 million years old. So that must mean old oceanic crust gets recycled. Remember, oceanic crust is a little bit denser which is more compact than continental crust. And so when that stuff interacts, the heavier stuff, the more dense stuff gets pushed down. So that's why the oceanic crust kind of subducts and gets recycled. So it doesn't stick around to get old because it gets recycled. And that kind of, the fact that proves that is that the oldest continental crust on the Earth is over 4 billion years old. So much, much older than the oldest oceanic crust. So that stuff, which we know if we just take a sample of it, is more dense. So that's the stuff that must be preferentially subducted. Continental crust can still get subducted. More on that in the next couple of sections in this unit. But when continental crust and oceanic crust interacts, the oceanic crust is the one that dives down. So when we look at the ages of the ocean basins, so the newest oceanic crust is this kind of maroon color. Here's the mid-Atlantic ridge, and this connected to the whole mid-ocean ridge system. It's all of this stuff. So this is the mid-Atlantic ridge. We can see the youngest rocks here in the center. As you get further away, they become more orange, and as you get further away, they become green and blue, as we see. So young rocks at the spreading center of these ridges, and the rocks get older on either side. This is just ages of rocks, not necessarily the magnetism. So putting everything together, putting magnetism, seafloor spreading, mapping the oceans, the ideas of continental drift, the mechanism of mantle convection, finally, plate tectonic theory is born. And it's based on a somewhat simple model, we can say that now, but a somewhat simple model that the lithosphere, the crust in the upper part of the mantle of the Earth, is rigid. It's made up of both oceanic and continental crust, as well as upper mantle material. It consists of variable size pieces called different plates, some big ones, some small ones. We saw that already. Plates may contain either all continental crust, all oceanic crust, or a combination of both. Oftentimes it's a combination of both. So here is, again, a map. For instance, the North American plate is made up of both continental crust, that's all of this stuff extending all the way out to the continental shelf, and oceanic crust, the stuff that makes up the type of rock that makes up the ocean basin. So we have both continental crust and oceanic crust that makes up the North American plate. Same with the African plate. We have continental crust and oceanic crust. But if you look at, for instance, like the Nazca plate, that's mostly oceanic crust. Or if we look at the Pacific plate, it's mostly oceanic crust. Not all, but mostly. Okay. So on this map, just as a reference, the numbers represent the average rate of relative movement of these plates in centimeters per year, depending on where you're at. For example, along the mid-Atlantic ridge, the North American plate is being pushed away from that mid-oceanic ridge, the mid-Atlantic ridge specifically, at a rate of 2.3 centimeters per year. That's about this much. North America is moving west about this much, about that much, this width every year. That's not much. All right. We'll look at more plate tectonic stuff in lab. So, kind of connecting all that together, plate tectonic theory, and boundaries. Remember, these plates interact. The lithospheric plates, they overlie the kind of hotter and weaker semiplastic asthenosphere, that other part of the upper mantle. Movement of plates results from the heat transfer system within the asthenosphere, the mantle convection. As plates move over the semiplastic asthenosphere, sometimes they separate and move away from each other, mostly at oceanic ridges. Those are known as divergent boundaries. Sometimes plates crash into one another, such as in oceanic trenches and other places. That's known as convergent boundaries. And sometimes plates grind side by side as they move laterally sideways past each other. And those are known as transform boundaries, where the edges kind of slide past each other. Now, what we're going to do in the next few sections in this lecture is talk about each of those. Divergent boundaries is going to be section 4. So I'll see you back here in just a second, to talk about divergent boundaries.